Okay, so we'll read out the question first, and it says that there are two circles that intersect at points A and B, and the arcs of each of the circles from points A and B on the one circle measures 30 degrees, and on the other circle it's 60 degrees. And we're trying to find the ratio between the two areas. So the area is a key thing. That's kind of what we're looking for, of the larger circle to the smaller circle. So we have two circles and a point A and B. One is at 30 degrees and one is at 60 degrees. So I always like to start by drawing out kind of exactly what it says, just to get a feel for what's going on so I can see it visually. So there's one larger circle, and then there's a smaller circle. They intersect, just as it says, at a point A and B. So I'll just get a different color here. Point A, and this is point B. These 2 points right here. And then we'll have two, obviously it's a circle, so it has a center. So we'll just kind of say this is the center. We'll call this one circle 1. This is number 1, and this is circle 2. Now, all right, so we have a little picture, and we go back to what we're trying to find. We look at the final answer we're trying to look for is the ratio of the areas between the two circles. So I think about how do we find out what is actually the equation for area, and we know that area is equal to, oh wait, I can use text, can I? Oh dear, I'll just draw this really quickly. Sorry. Big one, small one. Circle 1, circle 2. All right, back to where we were. So we know that the area of a circle is pi r squared. And then, so we're trying to figure out what the difference, how we can compare these two. So if we were trying to find, the only difference really between the two areas, because pi doesn't change, pi is just a constant, it's the two radiuses that are different. Radius of circle 1, let's try yellow. I have radius of circle 1, because the circle is the same on each side, is here. And then this is the radius of, I'm going to use green for circle 2. This is radius 2. And we know these are both radius 1. Okay, so in order to compare the areas between the two circles, we only need to compare the radius between the two circles because the pi's are the same. So we know that area is directly, that's kind of hard to read. We know that area is directly proportional to the radius of the circle squared. So what we want to do is we want to find some sort of comparison to compare the radius squared of find the comparison between R1 and R2. And if we can find some ratio to compare R1 to R2, we can find the ratio between the areas of circle 1 and circle 2. So we know that one of them is at 30 degrees, and one of them has an inner radius right here of 30 degrees and one of 60 degrees. We kind of need to figure out which one. And from the drawing, we can kind of see that the larger circle is going to need the smaller angle. That's kind of more clear to see if I had a more accurate drawing, but we can tell that this angle right here is going to be the 30-degree one, and this one right here. Where's my green? There's my green. That's the 60-degree. That's a 60-degree angle. So we have, but we have this kind of ugly shape right here. We have a kind of diamond shape, and those aren't really fun to deal with. But what we do know how to deal with really nicely, and we have lots of funky equations for them, is triangles. And we can make a triangle if we make a chord right here from A to B. So from A to B now we have this green triangle and we have this yellow triangle, which both kind of share this red side right here, which is a chord from A to B. And then we're like, all right, so where else can we progress from here? And we see that one thing that's really special here is we see this triangle right here, and it has an angle of 60 degrees. And we know with triangles that their total degrees always add up to 180. And seeing as this is 60 degrees, and we know that R2 and R2 are equivalent because it's a circle, so the radiuses are all going to be the same regardless as to where you're pointing to. These two are the same sides. This is the same angle, therefore it's equilateral. So meaning chord A and B also is R2. We have an equilateral triangle with a length of R2 on all three sides. So from here, now, hey, look at this. We have a triangle on the yellow side, which, let me draw this out outside the diagram just to make it more clear. We have a triangle with a 30-degree angle with radius R1, and we know that these two are the same because they're radius of a circle. So this is R1, this is R1, and on the chord that's connecting points A and B, we know that this is length R2 because we said we had the equilateral triangle between from the green one. So now we see we're trying to compare R1 and R2. So we're trying to look for some equation that we know that that kind of correlates the two of them in this kind of situation we have right here. And what comes to mind what's the kind of thing that we have when we have two lengths and one angle? We have sine law and we have cosine law. And cosine law is a little more appropriate here. So we can go ahead and I'll just write out what cosine law is. Cosine law is if you had if this was your angle and then you had if you had an uppercase letter as to represent an angle and the lowercase to represent the associated side, you have a squared equals b squared plus c squared minus 2 bc cosine of a. So in terms of the problem we have now, that's the general solution. In terms of the problem we have now, that means that R2 squared, R2 squared equals R1 squared plus R1 squared. Now they're the same, right? Because we have these sides, remember, are the same length. Minus 2 times R1 times R1. And we know R1 times R1 is just R1 squared. So we have the same thing again. Times by the cosine of A, which is the opposite angle. So this one right here, which is 30 degrees. So the cosine of 30 degrees. This was meant to say R2. Right. All right. So we can simplify this. R2 squared equals So r1 squared plus r1 squared, that's 2r1 squared, minus, we take, this is also 2r1 squared, and we know that the cosine of 30 is, I think that's square root of 3 over 2. But the 2's can, all right, so we have the square root of 3 divided by 2. We can simplify this further. This is r2 squared, and we know that that equals, we'll keep this the same for now, 2r1 squared, and then minus this 2 right here, and this 2 right here can cancel out. So we end up with just r1 squared times by the square root of 3. And then we can collect like terms. We know how to do that. We just we factor out the r1 squared, and you end up with 2 minus r1 squared multiplied by 2 minus the square root of 3. And then finally, we know that the ratio, we said earlier that the ratio between the two areas is going to be the same as the ratio between the two radiuses. So clearly we see here, between the two radiuses squared, sorry. So we see that the ratio between r2 squared and r1 squared is 2 minus the square root of 3. So that's kind of your final answer. Another way to kind of say it would be r2 squared over r1 squared equals 2 minus the square root of 3. And all I did there is kind of took this and moved it over, and that's kind of our definition of ratios, right? If one is if you divide one by the other, what you get is the answer. And then from here, I can just further prove that the thing I said earlier about how the areas are directly proportional to the radius squared. If we just multiply the top and bottom by pi of a fraction, we know that the top of a fraction, the bottom of a fraction, if you do the same thing to it, nothing changes. So you have pi times both sides, pi times r2 squared divided by pi times r1 squared equals 2 minus the square root of 3, just like before. Just put this in brackets to make it more clear. On both sides, on both the top and bottom. And hey, look at that, we have pi times radius 2 squared over pi times radius 1 squared, which is pi r squared of circle 2, pi r squared of circle 1. So finally, our final answer, we can determine that a2 squared over a1 squared, so their two ratios is 2 minus the square root, I'm running out of page here, of 3. And yep,